Okay, so I want to come back to calculating magnetic fields. And just a reminder of where we are. We've got the Biot-Savart Law, which is written here. And then for any situation where we want to know the magnetic field at a distance r from a current element, current I, length dl, we can go ahead and integrate that along a current carrying wire. And for example, we did it for a long straight wire and found that the long straight wire has a magnetic field magnitude mu naught I over 2 pi r, where r is the perpendicular distance from the wire. And the direction of that field it's around the wire according to the right-hand rule. Okay, so that's where we are. So let me go ahead and ask a question. An example. Let's say that we have a square loop carrying current I. It's got a side length A. And I want to know what is the magnetic field at its center. What is the magnetic field right there? How are we going to find the magnetic field there? Okay, so you need to think about that, how you're going to find the magnetic field there. So the way we would do it is we would find the magnetic field at the center point, due to each side, and add them up. So the net magnetic field is going to be the field to the top, vector addition to the field to the right, added like a vector to the field at the bottom, added as in vectorially to the field at the left. And so the net magnetic field in the center is those four fields added up. Now, actually, I got to be honest, sort of fudging this question a little bit. These are not long straight wires because the distance from the wire to the center of the loop is not small compared to the length of the wire, right? So let's just look at the top. This distance here is not small. R is not a lot less than not a lot less than A. So therefore, the top wire or any side is not really small compared to the distance R, and so it doesn't act like a long straight wire. But let's just approximate. So I got to give you approximate each wire as a long straight wire. Each side as B equals mu naught I over 2 pi R. Approximate the magnitude of the field to be a long straight wire. In reality, we would remember when we calculated the magnetic field due to a long straight wire, the limits we used were from minus infinity to plus infinity for a long straight wire. In reality, all we would have to do is go back and do that integral, but do it from this r to that r, right? So we're just doing for a limited or the length of, along the length of the wire. We would do it from minus a over 2 to plus a over 2, minus a over 2 to plus a over 2. So we would go back to the derivation for the long straight wire and change the limits from minus infinity to plus infinity to minus a over 2 to plus a over 2, plug it back into Wolfram alpha. Actually, why don't I just do that? Okay. So I went back and recalled what the integral was that we used. So I'm just taking a step back from this problem and saying, recalled what the integral was for a long straight wire. And I went back and put that integral into Wolfram alpha for a short straight wire, right, for just a length minus a over 2 to a over 2. You could go back to your notes or back to the video and check out what that integral was. And when I do that integral, what I get is the field for a long straight wire modified by this little quantity over here, 1 over the square root of a squared plus 4r squared, where a is the length of the side and r is the distance we are from the side. In this case, for the square, I do want you to note that r is a over 2. So what do we end up getting? Okay, apologies, I copied it wrong from Wolfram alpha. I missed when I wrote it down first that there's an a here. Okay, so I rewrote, so B for a given side, that says side right there. B for a given side, let me fix that. Once I use Biot-Savart Law and do the integral, I'm going to get mu naught, I rewrote it right here. B for one side is mu naught I over 2 pi r times a over the square root of a squared plus 4r squared. Notice that R is A over 2. So when I plug in, because R is halfway, right, it's in the center of the square, it's halfway down the length of a side. When I plug in R equals A over 2, if I plugged it in correctly, I get B, the final product. B is mu naught I over square root of 2 pi A. Okay. So I might have made an algebraic error. If I did, hopefully you caught it. If not, doesn't matter. We're just going to use this as the magnetic field of a single side. So if this is the magnetic field of one side, then we got to add up the magnetic field of all four sides. So let's go ahead. So if you got this problem for homework, I wouldn't necessarily expect you to do the integral. I would expect you to look up the magnetic field of a finite length of wire and then just add those four together. So you would sort of look up this equation and add those four together. But understanding where it comes from is important. So think about the top side now. So the top side has a magnetic field in the center of mu naught I over square root of 2 pi A. But what's the direction of that? Use the right-hand rule. Put your thumb in the direction of the current, which for the top side is to the current is to the right. So your fingers in the center of the loop go into the loop. Let's do that for each side now. Do the right side. Into the loop, do the bottom side. Into the loop, do the left side. Into the loop. All four fields go in the same direction. All four fields go in the inward direction. For each side, they go at the center, they go inward direction. I drew them offset, but they each point inward. So those four fields add like scalars. So what's the net result? The net result of the net field, it's 4 times the field of one side. 4 mu 0 I over square root of 2 pi A. So that's your answer. What's the field at the center? There it is. It's the field of each of the individual sides added together like vectors. Okay, one more example. Using Biot-Savart Law. What is, so this is going back, not a long straight wire anymore. What is the magnetic field at the center of a circular loop of wire with radius R carrying current I? So it's a fixed radius R, it's not a variable. What is the magnetic field at the center? So the magnetic field at the center. So we are going to use the Biot-Savart Law, right? dB. Okay, I wrote down the Biot-Savart Law. So the Biot-Savart Law in vector form is there, or in scalar form is the one below it. IDL sine theta over R squared, where the direction is given by L cross R. Okay, so that's the Biot-Savart Law. And so we need to write this for each current element. So I need to take a current element, DL, and that has a current which is pointing tangential to the loop. And so I need to go ahead and apply the Biot-Savart Law to what field that current has at the center. So that at the center, dB from that current element, dB at the center due to that current element is mu 0 over 4 pi. The current is I. The length of the current element is dl. And the angle between, remember that's the angle between L and R. The angle between L and R, hopefully you can see, is 90 degrees. 90 degrees, right? The angle between L and R, drawn it in there, is 90 degrees. It's the tangential direction, the radial direction, over R squared, and here it's a fixed quantity, capital R. So what is the magnetic field? That means if I now add up all the current elements all the way around the circle, right? Magnetic field due to a loop of wire. Oh, whoops. Before I do that, let me talk about the direction, and the direction given by L cross R. The direction of L cross R, L points tangentially, R points inward. The direction is out, right? So dB is out at the center. At the center, it's out. That's the direction right there. So we figured out the magnitude of dB, and the direction of dB is out. Okay, so let's go ahead and now find the magnetic field due to all the current elements as we add them up around the circle. So it's the sum of mu naught over 4 pi. Oh, Leif is there. Hold on, I gotta pause. Okay, sorry, I had somebody pop in on a meeting that was just running on my computer. Okay, so mu naught over 4 pi. Oh yeah, I was filling in just writing the integral sign. dl sine of 90 is 1 over r squared. So now we know that the direction of that is out in this case. So now we pull everything out of the integral. That's a constant. B is equal to, pulling everything out of the integral. Mu 0 is a constant. I is a constant. That doesn't change. 4 pi is a constant. And r is just the radius of the circle. So that's a constant for every current element. For each current element, r is the same, right? So no matter which current element it is. So all those are constants. We pull them out of the integral. And what we're left with is dl. The integral of dl, and the direction, again, I'll just carry that because it's a vector equation. So what's the integral of dl? It's the sum of all these little pieces. The sum of the lengths of all these little pieces. We don't have to multiply it by anything, so we don't have to find a relationship between any variables. But what's the sum of all these little pieces all the way around the circle? What is it? I can't hear you. What is it? What'd you say? Speak up. Okay, it is the circumference of the circle. So it's 2 pi r, the circumference of the circle, if you add up all those dLs. So what we're left with for the magnetic field of a circular loop of wire is mu naught I over 2r. The magnetic field of a circular loop of wire is mu naught I over 2r, and it's, according to the right-hand rule, it's out when the current is counterclockwise. What if the current was clockwise? Then it would be in, right? So in this case, it's out because the current is counterclockwise. If it was clockwise, it would be in. And again, this direction of the magnetic fields can just be figured out by the right-hand rule. The right-hand rule applies over and over again in different ways. So here we can use the right-hand rule in the way that we did up here to figure out the direction, or we can simply say, take your fingers and point them in the direction of the current, which curls around, and your thumb goes in the direction of the magnetic field. So if I put my fingers in the direction of the current counterclockwise, my thumb points out, so the field is out. If the current went the other way, clockwise, I'd rotate my fingers that way, and my thumb would go in. So in general, the magnetic field of a circular loop of wire is mu naught I over 2r, where the direction is given by the right-hand rule. Put your fingers in the direction of I, your thumb points in the direction of B. Okay. For the long straight wire, we put our thumb in the direction of I and our fingers point in the direction of B. Either way works. You could actually do that here. You could put your thumb in the direction of I and your fingers rotate around I. So actually, that's just another way to look at it. If you just put your thumb in the direction of I, your fingers rotate around I. So the field actually goes around, right, where it's out. Oh, sorry, it's in over here and out over here, right? So everywhere inside the loop. Can you see those? I think so. If the magnetic field circulates around this wire so that the magnetic field everywhere within the loop is out and everywhere outside the loop is in. So at the center, it's out. Okay. So this is the magnitude of the magnetic field at the center, mu naught I over 2r, and the direction everywhere within that loop is out of the board. Okay. Any questions?